Hello students, welcome to the course Nuclear Astrophysics. It has 20 hours lectures. So, you can see there are 40 files, each of about 30 minutes with plus or minus 5 minutes. And in this Nuclear Astrophysics course, I hope you have seen the syllabus of the course. It talks about the specific features of the union of nuclear physics and astrophysics. Some of you might have opted for nuclear physics separately. Of course, till plus 2, the basics of nucleus has been taught to you. So, the basics of nuclear fission when it comes to the nuclear reactions you might be aware of. And you also might be aware of astrophysics. So, if you have been taught the nuclear physics and astrophysics separately, then this course is really going to be helpful. Even most of you have not taken astrophysics course as part of your curriculum, it is perfectly all right, because the basics of nuclear reactions is going to help you to understand this subject. So, when you have opted this course, what are the questions which you try to understand from this course? What are the things that you are expecting to understand, and what are the questions that comes to your mind? So, let me float a few questions to start this course. Okay? Since time immemorial, it is quite fascinating in the night when you see before sleeping completely moon day or completely moonless day, you will see different beautiful pictures in the sky, and based on those stars and galaxies, sometimes if you see through telescope, so across the world in different civilizations, a lot of beautiful stories and fascinating narratives you can find in the literature. But of course, a human being a curious entity, always try to understand the properties of these stars and earth, and not only that, how elements are formed in the universe, how universe has evolved, what are the steps involved in synthesis of elements and evolution of the stars and galaxies, right. So, this beautiful photograph should give an idea about the interesting aspects of nuclear astrophysics. Okay. So, these are some of the questions which I am trying to put here to start with in this course. Okay. So, what are those questions? It is well known that a star like sun emits immense amount of energy, right. So, what is the source of energy emitted by the stars other than sun? Okay. And what is the evolution when it comes to the stars? So, how stellar evolution happens? Is there any relation between the mass of the star and energy emitted by the star, and also the size of the star? Will there be binary stars only, or can there be a clusters of stars? And when a star will die, in how many ways it will die? What is the starting point of any star? So, basically how stars do evolve. So, these are the questions that we will try to understand in this course. Okay? And why only a few stars undergoes explosion? So, when I use the word cooking of the elements, so it must be clear to you that lot of elements are synthesized within the star, lot of elements are synthesized within the star, whether it is a continuous process or discontinuous process, and where were the elements found on earth produced. So, many elements we see in our surroundings, how they are produced, what is the main reason behind it, and what is the relation with nuclear physics when we try to understand the origin of the elements that we see in our surroundings. All right. So, what are the things that we are trying to learn from this course? The fundamental ideas regarding nuclear processes occurring in stars. So, in this line I have given one of the important points of this course, that inside the stars whatever things are happening, they are basically nuclear reactions, right. So, what are the fundamental ideas regarding the processes linked with nuclear physics which are occurring inside the stars, and what are the observations one can make from the stars? So, stellar observations. So, first one is about nuclear processes which are occurring inside the stars. Okay. The second is observations of stars, and here we are going to see the role of quantum physics and important quantum mechanical phenomena which control the nuclear reaction. So, this is what we are going to understand from this course, and the nuclear reactions in a hot stellar plasma. At certain stage star becomes very hot, and what kind of nuclear reactions do take place inside the hot stellar plasma, and are there any stages for the burning of a star. Okay. So, stars while undergoing evolution, in how many stages the star will evolve, and what is the basis for categorizing the burning stages of the stars, that we will try to understand in this course. All right. And then what is the origin of elements in stars, how elements are produced in the stars. Finally, I will try to discuss and I will try to provide a brief overview of experimental aspects of nuclear astrophysics, so that we can understand the energy produced from the stars, and also to understand the synthesis of elements within the stars, synthesis of elements within the stars. Okay. So, one can summarize the goal of this course as to understand nucleosynthesis. Okay. Nucleosynthesis. What is nucleosynthesis? A process in which nuclear reactions take place, so that the transformation of one nucleus from another nucleus take place continuously. So, this process is called as nucleosynthesis, and this is one of the major goals to understand in this course. And second, energy produced in stars. How to do the calculations, and the basis for these two is nuclear reactions. Nuclear reactions. So, what are the prerequisites for this course? You should recollect the knowledge of nucleus that has been taught to you till +2, that is the energy emitted from a nucleus when another particle reacts with it. Recollect the knowledge of nuclear fission process. When thermal neutron reacts with the uranium-235 nucleus, it forms uranium-236 and it explodes. It is some kind of process in which we call it, in which fragments are formed. So, that process we call it as fission process. So, that requires understanding of nuclear reactions between two entities. And please recollect the knowledge of binding energy curve. When you plot the binding energy per nucleon versus mass number, then how it looks like, and what is the concept of binding energy, what is the concept of Q value of the nuclear reactions. So, these are the things that you have to remember, so that this course will be much easier to understand. And also the basics of alpha decay, beta decay and gamma decay will certainly helpful to you. And before taking this course, if you have done some experiments during teaching part, then that will be like value addition. Okay. So, let me draw the well known binding energy curve when you plot binding energy per nucleon. What is binding energy? The energy required to assemble nucleons into one nucleus, or the energy required to break the nucleus into constituent nucleons. You know very well, right? Binding energy per nucleon versus mass number when you plot. So, some kind of tentative diagram is like it is 8.8 MeV per mass number, and this corresponds to the iron, right, element iron, mass number 56, and there are some kind of peaks one can see here like hydrogen, helium, then lithium, boron, up to iron you can see, and after iron the binding energy per nucleon and it decreases slightly. Okay. So, this binding energy curve is going to help you in understanding various nuclear reactions and various features of nuclear astrophysics. So, let me start with the historical background of this subject, nuclear astrophysics. Okay. So, when people try to understand what could be the source of energy from the sun, what could be the source of energy from the sun. So, this was the thought based on which this field of nuclear astrophysics started. And in 1930s, around in 1936, Bethe and Christfield, they have proposed fusion of hydrogen into helium. Later, it has become part of a process called as PP1 chain. Okay. And Bethe and Weizsäcker, they have come up with a cyclic reaction, unlike a chain reaction in PP1, carbon, nitrogen, oxygen, which we call it as CNO cycle. And due to availability of reaction cross section based on the availability of facilities, accurate nuclear physics information became crucial for understanding the stars. So, Aston in 1910 or 1920s, he proposed, he has observed that helium as an entity, if you see the mass, is slightly, its mass is slightly greater than the sum of the masses of constituent nucleons. So, that was also can be considered as one of the starting points. And then when Cockcroft using the accelerator performed experiment, then it has given better idea about the nuclear reaction. The major problem, major challenge faced by people is following. By that time, the observations have clearly shown, have clearly conveyed the temperature of the stars. So, that stellar temperatures, though they are ranging from 10 to the power of 6 kelvins to 10 to the power of 8 or 9 kelvins, when the temperature is converted into the energy, and people also have seen the energy required for a reaction to happen, then there is a huge mismatch. What I am trying to convey is following. Okay. So, when you have nucleus 1, okay, having some protons and neutrons, and nucleus 2 having some protons and neutrons, when they try to react with each other, it has to cross a barrier, right? It has to cross a barrier called as Coulomb barrier. Then only a reaction can happen. That was the understanding at that time. So, the Coulomb barrier can be given as 1.44 Z1 Z2 divided by R in FM, femtometers. This is the separation between the two nuclei. This is the separation between the two nuclei. So, if the energy available is less than the Coulomb barrier, then reaction does not take place. That was the understanding at that time, right. At the same time, when Gamow proposed alpha decay, it was clear that though a particle which wants to come outside from inside the nucleus like alpha particle, or a charged particle wants to go inside a nucleus, though energy available is less than the Coulomb barrier, because of a quantum mechanical process called as tunneling, with which all of you are aware of, a reaction can take place. Then people thought, okay, because sun is having abundant hydrogen and helium, because of which energy might be coming from the sun. So, if sun contains hydrogen and helium, then because of the nuclear reactions, if energy has to come out, the available energy is able to cross the Coulomb barrier? No, because the stellar temperatures measured using a few techniques was less than, the stellar temperature giving rise to energy is less than the Coulomb barrier. So, people thought how a reaction can take place, but it is the quantum tunneling process which made people to get convinced that there must be huge amount of hydrogen and helium within the sun, and because of the quantum tunneling process, the reactions might be taking place and the energy is coming out of the stars, including sun. So, it is the quantum tunneling process which convinced people that reaction can indeed take place inside the stars, even though the energy available is less than the Coulomb barrier. So, this has prompted people to go beyond their hesitation that how reaction can take place. Then things evolved very fast after the particle accelerator initially started by Cockcroft and Walton. Okay. So, this historical background tells us that the curiosity to understand the energy emitted from the sun was instrumental in the evolution of this nuclear astrophysics course, and later it is a quantum mechanical process which made people to get convinced that yes, indeed reactions can take place. So, after providing this historical background, though astronomy is different, which is basically astronomy is about observation of the universe and astrophysics is the explaining the universe, right. So, astronomy deals with the observation of universe and astrophysics is explaining the features of these observations. Let me take some time to explain some basic features of the astronomy, though it is not directly linked with the nuclear astrophysics, but broadly it is linked with the subject of nuclear astrophysics. Okay. So, in this observational astronomy, we can easily divide the time before and after the invention of telescope. The first patent was filed in the year 1608, and we can divide into optical astronomy, radio astronomy and space astronomy. And under optical astronomy, if you see, the naked eye was replaced with the telescope, in which we have a lens and the light falling on the lens is focused onto a point, so that we can get an image, and the resolving power is given by the 1.22 into wavelength of the light and the distance d. Okay. And after the invention of telescope, at the focus still people were using the naked eye, even though eye can detect the various wavelength, it is not possible to store the data, right. Eye cannot store the data and it is not possible to see the fainter objects. Then we have prism and grating. This has provided information about the chemical composition of the sources from which light is falling on the telescope. So, it is basically the recording of the spectrum with the help of prism or grating, and the analysis of this spectrum has given information about the chemical composition of the objects which are emitting the light. Now, even prism and grating is used, the photographic emulsions which are able to store the things are suffering from some problems because of the inability to identify much fainter objects. Then the new light detection techniques based on photomultiplier tubes or silicon photomultipliers nowadays people are using many advanced photo sensors, okay, which made possible the detection of fainter objects. All right. The major challenges in this observational astronomy, especially in optical astronomy, you can easily expect the weather conditions which limit the observation times, and the atmosphere which absorbs the most of the electromagnetic spectrum, and turbulence in air, that is unsteady air, leads to the star twinkling. So, these are the challenges in the optical astronomy. Then coming to another type of astronomy, that is radio astronomy, where you deal with the long wavelength 1 mm to 15 mm, easy passage through Earth's atmosphere and interstellar gas. So, because of the ability of radio waves to pass through the different conditions when it comes to the weather, so it made possible even in the day or in the night one can do the measurements in this radio astronomy. But of course, the absorption of atmosphere, the absorption of large part of electromagnetic spectrum by the atmosphere cannot be avoided even in radio astronomy. And larger the aperture of the lens, you can see the more bright object. Because you know the brightness of the object at the focus of the lens is proportional to the aperture of the lens. So, researchers across the world, they try to build large size telescopes, but still they are suffering from the problem of absorption of large part of the electromagnetic spectrum by the atmosphere. Then we can go for space astronomy, because the ability to put the instruments, the telescopes or detectors in space made possible to get rid of the problems that arise due to the atmosphere, which is absorbing large part of the electromagnetic spectrum and the background light. Okay. Anytime it can be done, and there is no problem of the unsteady air, all right, and there is no condition on the observation times as well. So, one can go for balloons. You might be aware of, there is a balloon facility in India at Hyderabad. It is TIFR, Tata Institute of Fundamental Research balloon facility, where one can put the instruments within the balloon and take it to some height and collect the data. So, above earth surface you can go to some distance, and one can use the rockets, and one can put the instruments inside the satellites which can collect the data, and in space laboratories using telescopes and other instruments one can collect the data. So, the advent of space astronomy has made possible the study of the universe by absorbing the wavelength of all types of ranges which are there in the universe. So, the astronomy we can categorize mainly into space astronomy, radio astronomy and optical astronomy. So, these are all basically observational features, all right. And in coming times we can expect astronomy based on neutrinos. Why neutrinos are important? Because if you remember beta minus decay or beta plus decay, that has been taught to you. So, neutrinos, they are very difficult to detect, it is not very easy, and the sun emits large number of neutrinos. The fusion of hydrogen and helium, they cause the emission of these neutrinos, and the detection of neutrinos can help us to understand the evolution of universe in a better way, and the detection of gravity waves. So, these are the neutrinos and the gravity waves which can take this field of astronomy to next higher level. And if you see the observed structures in the cosmos, let us start with the solar system, okay, which contains the sun and also many smaller bodies, all right. you can see planets with their satellites, you can see asteroids, you can see comets and meteoroids revolving around it. And stars, they are nothing but hot gases, they follow the laws of pressure, temperature and density, and planets are cool objects. Okay? While stars are hot gases, they can be categorized into hot gas entities, whereas planets are cool objects. And let me give you some quantitative details about the properties of the sun. About 7 lakh kilometers, if you see the sun radius, and mass of the sun is about 10 to the power of 33 grams, and the density is about 1.4 grams per centimeter cube, and the surface temperature of sun is about 5800 kelvins. So, from now onwards in this course, whenever you come across a circle with a dot at the center, so that denotes sun. Because when we deal with the mass, luminosity, that means energy emitted by star per unit time, we always try to say in terms of mass and luminosity of the star. So, this symbol is going to travel with us throughout this course. Okay? Some more numbers: energy emitted per unit time, luminosity, it is about 10 to the power of 33 ergs per second. In terms of mega electron volts, if you see 10 to the power of 39 mega electron volt, you can imagine the amount of energy emitted by the sun. And it has been seen that this emitted energy, emitted by the sun per unit time is found to be constant throughout the history of the sun. Of course, the wavelength of the light coming from the sun is not limited to only visible range, but entire electromagnetic spectrum, And we are also aware of solar wind. It basically consists of ions of variety of atomic species, predominantly hydrogen. So, many times the solar winds also gives some important information about the nuclear reactions taking place within the sun. And of course, neutrinos, one of the important quantities coming from the sun in a good number. And the understanding of interior of the sun, till now we are able to do only based on some solid theoretical arguments, to some extent from the observation of the neutrinos. Why interior of the sun can be understood only from theory, why not by the experimental observations? Because as I said, sun is full of hydrogen and helium, and the reaction between proton and proton is proved to be impossible, at least with the available technology. So, because experiments cannot be done when it comes to the reaction between two protons, the interior of the sun can be understood only based on some solid theoretical arguments, and partly by observing the neutrinos. Fine. So, after discussing the solar system in the observational structure of the cosmos, let me go into stars, a collection of stars. Earlier I have discussed only about the one star, that is sun. Here I am going to discuss about the stars. So, what you would like to hear regarding the stars? How many stars are available, and what is the mass, the range of the masses of stars? What is the range of the luminosity of the stars, and how they are related to the mass and the luminosity of the sun? So, let me provide some kind of quantitative information in this slide. So, to give you an idea about the observational structures in the cosmos, starting from the sun in the solar system, then I am going to collection of stars. Okay? If you see the mass range, mass of a star divided by mass of the sun, m by m sun is ranging from 0.1 to 100, though majority of them are comparable or less than m sun, that is m by m sun is less than or equal to 1 for majority of the stars observed. All right. And if you take mass of the stars which are greater than sun by maximum 10 times, they are rare. Okay. And m by m naught greater than or equal to 100 is not observed till now. Okay? They have not been identified stars whose masses are 100 times higher than the mass of the sun, they have not been identified till now. So, this information on the mass of the stars is very important in this course. Who decides the mass of the star, and when the mass of the star will change, what is the upper limit of the mass, what is the role of nuclear physics inside it. So, that is what we try to understand in this course. Okay? So, as of now I have given information about the mass of the stars when compared to the mass of the sun, of course, which is also a star. Okay? And if you go for the stellar temperatures, temperature of the stars, it ranges from 3000 to 50,000 Kelvin. Okay? That is why we call them as power plants and also cooking pots of the universe, based on which you can see one of the important references of this course, cauldrons in the cosmos, Rodney and Rolf's authors. Okay? Cauldrons in the cosmos is one of the standard textbooks in the field of nuclear astrophysics, other than nuclear physics of the stars, that is written by Iliadis. Okay? Now, if you see the sun nearest stellar neighbor, it is about 4 light years away. 1 light years is about 10 to the power of 15 meters. See the separation between the stars. So, when we consider sun, its nearest neighbor is about 10 to the power of 15 meters into 4. That means 4 light years away from the, of course, multiply with 9.4 also. So, we can say like 37 into 10 to the power of 15 meters away from the sun. This is the nearest neighbor. So, you can imagine the separation between the stars in the at least our own galaxy. All right. And measurement of the interstellar distance, how this distance is measured? When I say nearest neighbor is 4 light years away from the sun, by standard trigonometric method that surveyors use even on earth to measure the distances. Okay? But this surveyor technique is valid only up to 30 light years, and for larger distances some indirect methods have to be preferred. Now, it is very clear to us that stars are not in fixed position. Okay? They are relative to one another under the influence of gravitational force. And if you see the data of luminosity L by L naught, it ranges from 10 to the power of minus 4 to 10 to the power of 6, whereas mass range is 0.1 to 100 and the temperature is 3000 to, I will check in the next lecture whether it is 5000 or 50,000, I am a bit doubtful. Okay? Anyway, so the L by L sun, you see this L refers to the star. Okay? 10 to the power of minus 4 to 10 to the power of 6. The range is quite large, it is about 10 to the power of 10, whereas the mass range is, you see, only 1000, 0.1 to 100. So, why is so much difference in the luminosity range when there is less range in the mass? So, this is a beautiful relation between the mass and luminosity of the stars. So, L differs very greatly, and if you see the spectrum of the light emitted by the stars, as I said earlier, it provides information about the chemical composition, and it has clearly established beyond any doubt that hydrogen is most abundant element followed by the helium in the stars. And we use the word metals in the case of stars when carbon and beyond elements starting from carbon and beyond they are present in the star. If they are more, we can say metallicity of the star is more. Okay? So, carbon and beyond elements, carbon and beyond, we term them as metals in this field of astronomy. Okay? And we can categorize into 2 types: population 1 stars which have high metallic content and we consider them as young star, and stars which are having low metallic content, they are called as population 2 stars and they are quite older. Okay? And sun belongs to population 1 star. Okay? So, more about the structure of the cosmos in the next lecture. So, to summarize today's lecture, we have seen the historical background of the nuclear astrophysics, and what we are going to learn from this course, that is how nucleosynthesis happens inside the stars and how the energy production in the stars can be understood. These two are the important goals of nuclear astrophysics. And then we have seen the salient features of observational astronomy, that is optical astronomy, radio astronomy and space astronomy. Then some observation structure in the cosmos. We have seen important properties of the sun and the stars. Then I will go beyond the stars, that is galaxy and then the universe. What are the properties? I will try to convey in terms of some numbers. Hope you have enjoyed this first lecture, and I am hopeful that upcoming lectures also you will enjoy. Thank you very much for your patience.